Ladies and gentlemen, hello and welcome. Coming to you not quite live from One Take Studios, where today's topic is introductions to random variables and probability distributions. That is a mouthful, and about half of what we're doing today is vocabulary, just trying to understand some of these things. So let us begin with our vocabulary. For starters, we are going to talk about a statistical experiment, or it could also be a statistical observation. What is this? All right, this is just any process by which measurements are obtained. So if we run an experiment, we collect data, it's a statistical experiment. Yay, awesome. Next, what is x? And this is a reoccurring question because we have a lot of formulas where x takes on multiple meanings, or at least multiple values. And this is kind of an explanation of that. X represents the quantitative results. So notice we're obtaining measurements and we're looking for quantitative. We're talking about numbers here. Okay. Can you observe numbers? In some cases, yes, but this is not qualitative. This is only quantitative data. And so X represents each of our quantitative values. All right. What does it mean if X is a random variable? And let me take a moment and highlight those words, so to speak here, random variable, because that's really the vocabulary in this sentence. X is considered to be a random variable if the value that X is holding the place of is going to be a chance or a random outcome. All this is saying is that X's are still X's and they still represent all of the quantitative responses, but if we have some sort of probability, chance, randomness attached to this, then they are going to be random variables. And I'll show you an example of that here in a moment. We have what are called discrete random variables. Discrete values are finite or countable. And this is saying that we have a finite or countable number of values. Countable. 1, 2, 3, 4. This is something that you can actually count. So I can count how many x's there are. I can count how many values there are. As opposed to a continuous random variable, where we have a countless. Literally, we cannot count the number of values in a line interval. So a difference between these two. Oranges and orange juice. I can count oranges. Oranges could be a discrete random variable. The orange juice itself, how do you count the juice? Because not glasses of juice, because if I was counting glasses of juice, that would again be finite. That would be a discrete variable. But the juice itself, well, I've got some place between 4 ounces and 8 ounces, and I might have 4.72 ounces. And as I drink it, I will have less ounces, and it will not be a countable amount due to all the decimals and fractions. Continuous random variables are more fluid, sometimes literally fluid, like juice, but not always. If you are counting things 1, 2, 3, 4, 5, discrete. If there's any sort of decimals, values between them, the amount of gas in your gas tank as you fill it or as you drive type of thing, anything that can change by fractions and bits and pieces, this is going to be said to be continuous. All right. The biggest thing today is right here. All right. Probability distribution. This is our big overall topic here. And believe it or not, it's something we've seen before, but naturally we're going to call it by a different name just to make life more confusing. We are assigning a probability to each distinct value or interval. In other words, I have these random variables, I have these values, and each one has a certain likelihood of happening. And if I find out what the probability is for each of those things, I know what the distribution is for my probability. This is the same thing as relative frequency. If we go back quite a bit to our frequency tables, we were finding our probability distribution when we did relative frequency. We're saying here's all the classes of data, and here's how likely it is for this one to occur, and here's how likely it is for this one to occur. And we made these cool graphs on our frequency tables. They were called histograms. That is simply a probability distribution. If you have a relative frequency graph, that is a probability distribution. And so often we are using histograms to make this happen. All right, so what do we have? We have a basketball player, because I don't know why my brain always goes back to basketball for this, but it kind of does. And this person is shooting 100 sets of 5 free throws. They're probably not doing this all the same practice, so this would be the kind of data that you accumulate over time. But 100 sets of 5. Think about this. What could happen? All right, you shoot 5. You could make all 5. That could happen. You could make 4 out of the 5. That could happen. You could make 3 out of the 5. That could happen. Each of these is what we would consider to be a random variable. All of these things are things that could happen as a result of shooting a set of 5. How many outcomes is that? Did you say 5? Because think about that. You could make 0 free throws. 0, 1, 2, 3, 4, or, oops, one more finger, 5. There are 6 outcomes here because you could make 0, 1, 2, 3, 4, or 5 of the free throws. And we're going to look at the distribution, what that could possibly appear as. And so, here we see our x values, which is going to be the number of shots made. All of these things are the things that could happen. I could make 0, I could make 1, 2, 3, 4, or 5 total in each set of 5. Collecting data, all right, let's say that we've been tracking this person and only one time did they miss all of the free throws. 23 times they made 1 out of 5. 35 times they made 2. 22 times they made 3. Is this an NBA player? Probably not. Could this be me? Yeah, maybe. And so these are all the occurrences, the frequency of each of these things. If you'll notice, 1 plus 23 plus 35 plus 22 plus 13 plus 6 equals 100. So this is all 100 of our outcomes. So if we are then looking at the probability, again, all this is just the relative frequency. And because I chose 100, I just made our lives happier. Because what is 1 out of 100? That is 100th. What is 23 out of 100? That is 23 hundredths. Which these are also then probabilities. There is a 1% chance that this person will make 0 of their shots. And we just kind of keep on going down the line. 35 out of 100, 22 out of 100, 13 out of 100, 6 out of 100. These are all the probabilities based on data that's been collected for what could happen making 0 through 5 shots. This is my probability distribution. This is the frequency at which it occurred. And obviously, the more sets of data that you collect for this, the more information you have, the more accurate these things are going to be. I could make a histogram. These would be the heights of all of my bars right now. Ooh, what would be on the x-axis for my histogram, though? Because 0, 1, 2, 3, 4, 5. If you remember histograms, the bars are like smack dab next to each other. There's no spaces between them. So you'd have to actually go a half point bump out each direction. So the bar at 0 would have to go from negative 0.5 to 0.5, and that would be its height, 1%. The bar at 1 would go from 0.5 to 1.5, having a height of 23%. 2 would have to go from 1.5 to 2.5, and so on and so forth down the line to closing those gaps to create a true histogram and not just a bar graph. All right, let me ask you this question. If this is somebody's record of what's happened in the past, and these are the likelihoods, the probabilities, if this person was going to shoot 5 free throws again, what would you think is likely to happen based on all of these probabilities? Could they make all 5? Yeah, it's possible. It has happened before. Could they miss all 5? It is possible. It's not super likely. But where are my higher probabilities? Right about in this range here. And so that brings us to our next thing. Probability distributions have means and standard deviations, just like other data sets do. But it makes life a little bit interesting when we take a look at these things. All right? So, right there, that's what I want. There we go. Means in the world of probability distributions are not referred to as mean. They're referred to as expected values. Here's what I would expect to see as a result of this. We are still using mu for mean. This is the sum of all of the x values times their probabilities. So if I'm looking at this setup here, here's my x value number 1, 0, times 0.01. 1 times 0.23. 2 times 0.35. Each x value, each of our random variables, times its probability and add them all up. Does anybody think that this looks familiar? Do you know what this is? These are weighted averages. We've talked about these too. So all a mean is a weighted average. Rather than just adding up 0 through 5 and dividing by 6, we're saying no, because some of these things are more likely to happen and some of these things are less likely to happen. Can we calculate this by hand? Yes, we can. I'm going to show you something else here in a moment, so hold on a second. Standard deviation is still called standard deviation, so good for us, the language didn't change there. But this is our new formula based on these current circumstances. Here's sigma, and square root of the sum. We're doing x minus mean, x minus mu, so we're talking each of these, we're looking at how far is the value from the mean. The mean would be this guy right here, by the way. Squaring that amount, and then again multiplying times its probability, putting its likelihood into the mix with this. This used to have to be done in steps, in like tables to keep things organized, because quite frankly, calculating this one's a pain in the butt. This one's sort of possible. This one is not fun at all. So what will we do to make this happen? Well, all right, let me switch over my screen and let's take a look at this, shall we? Here is my calculator. And again, I have opened a spreadsheet on a new document. And I'm going to put my x's in the first column. So we said that we could make 0 shots. Oops, can I make it there? Right there. Give me that 0. There we go. I might make 1 or 2 or 3 or 4 or 5. So those are all the things that could happen as a result of shooting 5 free throws, which by the way would be considered to be my sample space. Yes, those are all the possible outcomes. And so these are what we consider to be all of my random variables then. In the second column, I'm going to put their frequency. So 0 actually occurred one time. Okay, great. Making 1 of the 5 shots occurred 23 times. 35 is how often we made 2 shots. 22 is how often we made 3 shots. 13 is how often 4 shots was made. And 6 is how many times 5 shots was made out of 5. So in the first column, these are all the things that could happen. These are our random variables. And in the second column are the frequencies. You could actually write these as frequencies, or you could write these as relative frequencies, and either way it would work. So pick one or the other. If you recall, everything fun and exciting is in the menu. And we are looking for statistics right now, and we are trying to run some calculations. One variable stats previously has given us mean and standard deviation. I want to go there again. Even though I entered 2 columns worth of data, I want one variable stats. And when it says how many lists, I still want to say one list. I have only one list of variables. That's that first list, 0, 1, 2, 3, 4, 5. However, here's where things change. All right, where are my x's? Where is my list? It's actually in column A, so if you follow my cursor here for a second, I like to do it this way, hit the A, and then go control, funny hard brackets. That means that it's going to read all of column A as my x values. We have ignored this entry before, because all of our frequencies were 1. All of our frequencies are not 1 this time. So we're going to say, hey, I would like you to refer to everything in column B for my frequencies. So B, and then again control and those hard side parentheses. There we go, so it reads column. So here's where my x's are. Here's where my frequencies are, and we're going to deposit the results in column C. What do we have here? Let's see. I'm going to scroll back up for a second. All right, so there's our one variable stats. Ladies and gents, there's x bar. That's mean. So x bar, mu, you could write it either way. The calculations are the same. It's 2.41. Which, if you think about it, if you go back and look at our probabilities, we said, hey, what occurs the most often? 2. Most often, we make 2 out of 5 free throws. And so this is 2.41, indicating that there are several things that have happened above 2, so I would expect my expected value, my expected value, to be between 2 and 3 shots, because this is what's going to be occurring most often. So expected value should always make sense, and it is a mean, but it's a weighted average, so to speak. Scrolling, scrolling, scrolling. Please notice again, I'm going to go back up too. I have both S and sigma. Again, these are both standard deviations. If this is a population, we should be using sigma. All right, so there it is, and there are the calculations. This has a standard deviation of 1.18 if I'm rounding, which is actually really close to the standard deviation here. So standard deviation is still a measurement of the spread of the data, but in this case, it's almost like a measurement of risk. Because we're saying, based on probabilities, it is relatively likely, scooching back up here for a moment, scooch, 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 it is relatively likely that we will make 2 or 3 out of our sets of shots for the free throws with a standard deviation of 1. That's not that big of a number, so we can expect that we're going to be, most of the time, within 1 shot of this. And the larger this is, well, that just means that the frequencies were more spread out, and we would have less surety of what's going on. So hopefully that made some sense to you, I hope. But yeah, that's it. So random variables, probability distributions, it's really just relative frequency, and there we got the calculator to help us out. So thank you, Lord, for those. All right, thanks, guys. Have a good day, night, evening, morning, whatever you got.